we can see that it's not straight up, but it's on an angle. That makes it much easier for the part to be taken off of it. If it's straight up and down, straight 90 degrees, the material tends to want to stick to the plastic sticks to the mold, and it's real hard to get out of it. That's one of the problems we have when we do our plaster molds. If they have a straight side to it, it's real hard to get that part off. And just think of it, if it was less than 90 degrees, you wouldn't even be able to get it off because it'd be stuck on there. But usually that draft angle is a couple degrees to about 7 degrees. Just a little bit of an angle helps get that part off. Sometimes we'll even take a air hose and blow air between the part and the plastic. That helps kind of separate it. Another term that if you run thermoforming parts you'll become familiar with, it's called webbing, and that's excess material in the corners of the finished part on a male mold. If this was our part, you would have material kind of sticking out this outside, kind of extra material that doesn't go along the actual mold, but kind of sticks out. And that's generally a defect. Doesn't look good, usually weak there, and we want to try to eliminate that as much as possible. And then vents, holes drilled through the bottom of the mold into the cavity to let air escape. So here you can see the little hole. These little holes allow this would be a vacuum mold, allow the air that's on the top to be sucked out because there'll be air trapped in between the plastic sheet and the mold. If it stayed trapped in there, you wouldn't get a good contact between the plastic and the part itself. So those air vents allow the air to come out and get a good contact between your mold and your plastic. So you get good, distinctive, well-formed parts. They need to be small enough not to show up in the part, but large enough so you can get all the air out quick enough, depending on how fast your process works. Because you'll see when even our machine, which is a small machine, as soon as you turn the vacuum on, it sucks that plastic on really quick. Thermoforming, the faster you can do it, the better. It's best if located in the lowest sections of the mold so you can get all that air out of the lowest section. Help you make the best quality part. Just like any other process, there's advantages and disadvantages. Advantages is low machine cost. Generally speaking, thermoforming machines are relatively simple, relatively inexpensive for the size of the parts you're going to make. Low temperature is required, because in thermoforming, we take sheet material that's already been processed through an extruder, and then we heat it up so that it's soft, but it's not enough heat to melt it. Instead of going 400 degrees, maybe we'll heat it up to 200 degrees, where it becomes soft and pliable. Then we can shape it. I remember back when I was a kid, I had a machine, it was a little vacuum former, where you could take these little plastic squares and little metal molds, and you put the mold on this thing, and you kind of like our thermoformer, clamp the plastic on it, and you closed it, and you heated it up, and you pumped it up a little bit, and it sucked the air out of it, and you made little plastic toys. Same process, basically. Low mold cost. There's no movable parts in them. They're not made out of steel, tool steel. They're just made out of usually aluminum. Relatively inexpensive for molds. Low pressure is required. Typically, air pressure is used. If you use a vacuum pressure, you know what the highest vacuum can be? Really, when you use vacuum pressure, the pressure you're using is air pressure. You're just evacuating the air. So the normal air pressure in the room actually forms it. Atmospheric pressure at sea level is 14.7 psi. So that's how much pressure we're talking about. Not much when you compare it to injection molding, which may be 5,000 psi. So it's much less. And even if you have pressure forming, the pressure may be 90 to 150 psi, but certainly much less than other processes. Large parts are easily formed since it's a simpler machine. The molds are inexpensive to make. It's easier to make large parts without being too awful expensive. And since we're not cooling it from 400 degrees, we can have relatively fast cycle times. So those are the advantages of thermoforming process. There are disadvantages. One of them is the high cost of raw materials. If you buy your sheet material, for instance, it can be expensive. A lot of processors that do thermoforming at Kerwood here in town have their own extrusion lines that make the sheet material, and then they process it into thermoforming parts right there. And why that's important and makes it less expensive is there's a very high scrap rate associated with thermoforming. Because if you think, say, that mold there, if we made it on our machine, and this is the size of the sheet, it's about 18 inches, I think, by 18 inches. If we made one part, you can see it's a lot bigger. All that material that doesn't make the part pretty much is scrap material that has to be ground up and re-put in the process, or if you can't do that, you have to get rid of it. That can add up to a lot of cost. Most places, like Kerwood, takes all the extra material. They try to maximize the web usage. They still have extra. They grind it up, put it back in their extrusion process, and then remelt it and rerun it. Only one side of the part is defined by the mold. The side of the sheet that faces the mold has the good texture that is wanted. The outer side kind of follows it, but it may not be exactly the same texture as the inner side. So that one side is only defined by the mold. In injection molding, for instance, the whole part is defined by the mold. The whole part touches the mold. Inherent wall thickness variation. When we're forming the part, we start with a sheet that is pretty uniform. Then we make parts of that sheet move. The part of it that moves the farthest gets thinner. Parts of it that doesn't move the farthest stays the thickest. Similar blow molding in that regard is you can have a thickness variation. And you'll see if we make parts like this one here, you'll see down in the corners is where it stretches the most and it becomes the thinnest. This mold right here is a mold that you would make for packaging, say for cookies or something like that. And if you get cookies like that, you notice that in the corners there, they'll tend to be much thinner. Break, that's where they'll break. That's because it stretches more in that area than it does on the sides there. So it has inherent wall thickness variation. Internal stresses are also common with thermoforming parts because you're stretching it while it's warm, fairly hot, but not certainly at its melting point. So you're kind of forcing the polymer molecules to stretch and move when they probably don't want to do that. We think of back, we talked about polymer molecules being like springs. When you're forcing it to move and stretch, it's like pulling those springs, then you cool it, and they're frozen in tension. So they have stresses already put into them. They become weaker there. What you would see is if you put that material in an oven again, you'd see that it would relax and try to go back to its original shape. We can do that even when we run our thermoformer. If we run a part and say there's some defects in it, as long as you didn't put a hole in it, you could actually take that sheet, put it back in the oven, and watch it go back to its original shape, and then do it again. You can do that within reason, as long as you don't stretch it too much or put a hole in it. Once you put a hole in it, then it's no good. You can't form it because there's no seal. You can't form it. This is how the plastic sheet material behaves in the oven. And we start out with a fairly flat sheet there on top. Take it from room temperature. On our machine, we clamp it in. This is how the plastic sheet material behaves in the oven. And we start out with a fairly flat sheet there on top. Take it from room temperature. On our machine, we clamp it in. It slides back into an oven, and the oven's pretty much like a pizza oven. It has heating elements on the top and bottom of the sheet. So after it goes in the oven, we set it for a certain temperature and a certain time. Once it starts heating up, you'll actually see, like in number 2 there, ripples going across the plastic material. And what's happening are those stresses that were put in when the sheet material was actually extruded are starting to relax. So you see those ripples go across it. Then eventually it'll get tight again. After it gets tight, you keep adding heat to it because it's still a little bit stiff in that case. It's not soft enough probably to mold. You keep heating it for a while and you'll see it start to droop. Once it starts to droop, that's a good sign is you better get it out of the oven, because if you leave it in the oven longer, it'll keep drooping and it'll eventually break. And there's screens, wide mesh screens over the oven elements, but if the plastic hits that screen, it'll get stuck there, and then if you leave it there, you can actually start a fire. So when you're running the thermoformer in class there, you want to make sure you get it out when it's here and not like that. Especially if it starts coming out and it gets caught on there, it just makes a big mess. And you have to take that screen material, which is kind of a pain to get it out of there, and take it in outside and get the torch out and burn all the plastic off of it. That's about the only way you can get it off of there, is by burning it off.